Our goal is a motion planner for assembling magnetic modular cubes. These modules are cube-shaped, with magnets embedded in the faces. Changing a global magnetic field can make the cubes rotate in place or pivot walk. At left is one hardware trial. At right is our simulator that began in the same initial configuration. Due to stochastic effects, the simulator tends to diverge from the hardware and is best for short time horizons. Here we have 2 blue and 2 red cubes. The objective is to assemble into the L shape shown in the upper right. To achieve this goal, the planner constructs a graph consisting of polyomino sets as nodes and connects cube pairs that should create these sets in the workspace. The local planner attempts to connect S7 to S6 with success. Trying to connect S6 to S2 results in failure due to unusable subassembly. Connecting S6 to S3 also fails. Now we fall back to the initial configuration because there are no options left. Connecting S7 to S5 gives success. Connecting S5 to S1 is also successful. The local plan connects S1 to ST, choosing to pivot walk to the bottom boundary, and the target is assembled. Here is a larger example with 12 cubes of red and blue type in the workspace. The objective is to assemble into the A shape shown in the upper right. The planning process took 43 seconds to compute. A local plan connects 2 cubes together. The 2 cubes to be connected are marked with yellow. The local plans are concatenated by the global planner. At the end of each local plan, the number of polyominoes decreases by at least 1. While connecting the 2 cubes at center, the local planner generated the 3-cube column at bottom left. This shortened the plan length, so the full assembly only required 10 local plans. Our paper analyzes how structure size and shape affect planning time. This video shows the result produced by the global planner. It is not the planning process itself, which took 43 seconds to compute. There are many applications of this work. In this video, 2 10-cube magnetic robots are assembled into a 20-cube structure. Though every cube is steered by the same global magnetic field, collisions with the workspace stop the left structure and enable joining. The resulting structure is mobile and can be walked around and rotated. These assemblies can be used for capturing other objects and transporting them. Here, a 5-magnet column becomes the top of a 14-cube box. They capture this red cap of a whiteboard marker and can transport it to desired areas of the workspace. Our robots can only pivot walk sideways, so movement in other directions requires rotating perpendicular to the direction of travel, pivot walking, and then rotating back to the desired orientation. In this video, a 7-cube U-shaped robot combines with a 13-cube cup-shaped robot. The cup can transport the 3D printed object. When assembled, the 20-cube robot can manipulate the object, controlling both its position and orientation. Once the task is complete, a fast 90-degree rotation of the magnetic field disassembles the magnetic structure, and the resulting pieces can be reused for another structure. Modular cubes with embedded magnets can also be used as reusable masks, as demonstrated by this lithography using photo paper, where an unexposed image is left behind. Our new work is an improvement over our previous algorithm that required the cubes to start and end on integer positions and only use 90-degree rotations. With these greater freedoms of representation, we can solve more problems and find shorter solutions. A key takeaway from our simulations is that the planning difficulty strongly depends on the output shape. We gave our planner up to 600 seconds to plan assemblies. We conducted 100 trials for each setup and compared 3 sorting strategies. The average results are shown. In general, multi-row horizontal shapes are hard. The times for all trials that succeeded are shown at top. Columns are easy to plan, but horizontal shapes take longer. Here are similar results for more complicated shapes with 11 to 12 cubes. 1 cube thick lines are easier, such as the C shape, but the thick plus shape is hard. Up to 40% of trials with the plus shape timed out, and the successful trials took an average of 250 seconds to plan, as compared to 40 seconds for C. Caves and holes do not impact the performance of the global planner. Our solver is available on GitHub, and we welcome collaborations. Come visit Aaron's lab in Houston, Texas, or Kjell in Braunschweig, Germany.